a competitor, Moritz, from the Lycée des Garçons Esch, with his project Quantum Mechanical Description of the Electrostatic Force. The aim of his entirely theoretical project is to illustrate a model which allows to approximate Coulomb's law describing the interaction between charged particles by using a quantum mechanical approach. But let's have Moritz explain it.
Hello everyone. Today we are going to quantum mechanically analyze the electrostatic force. As you may know, there are four fundamental forces of nature, which are the weak and strong nuclear interactions, the gravitational force, and the electrostatic force. Each of those forces can be described in quantum mechanics by the exchange of particles which are called force carriers. I'm especially interested in quantum electrodynamics, and this model uses the exchange of so-called virtual photons to describe the electrostatic force. However, even if it provides really good results, it is also quite complicated. And therefore, I wanted to develop a new model which uses only basic quantum mechanical techniques and nevertheless provides a good qualitative description of the quantum mechanical electrostatic force. I then, of course, also analyzed the limitations and the accuracy of such a model. But let's start with the general characteristics of a quantum mechanical system. A quantum mechanical system can be in different states, and each of the states has a well-defined energy. The energy of a state is related to the amplitude of the probability for making a transition between two states, and the energy properties of the system can be described by a matrix called a Hamiltonian. The Hamiltonian carries all the information which is necessary to describe the system and also the information about the energy of each of the states. This is the piece of information we are most interested in because from it we can calculate the force which acts on the particles. So let us consider a first example, two electrons on a straight line which repel each other. According to my model, each electron can be given a special property, which means that it can be either in an E state where it can emit a virtual photon or in an A state where it can absorb a virtual photon. The system has then one electron in an E state, which emits a virtual photon and therefore turns into an A electron, while the other electron is in an A state and absorbs the virtual photon and therefore turns into an E electron. The amplitude for such a transition is called A here in the presentation. The system has then two base states, one state where the first electron is in state E and the second in state A, and a second state where the first electron is in state A and the second electron in state E. From these considerations, we can calculate the Hamiltonian, which you see here above. The EO stands for the zero energy level of the system. The Hamiltonian then allows to calculate, by applying some basic quantum mechanical formulas, the energy of the system as a function of the separation between the particles. This function is drawn behind me, and you see that when you increase the distance between the particles, the energy of the system decreases. As you may know, a system always tends to the state of lowest energy, and since the state of lowest energy corresponds in this case to the state of largest separation, the system wants to increase the separation between the electrons. That is only possible if there is a force between the electrons which repulse each other, and by that we have quantum mechanically proven that there has to be a repulsive force between two electrons. I then proceeded with more complex systems like 3 electrons at the corners of an equilateral triangle, 3 electrons on a straight line, and also 2 electrons and a proton on a straight line. In this last case, you can also analyze the interaction between particles of opposite charges. In each of those 3 cases, I found the right qualitative results for the force on the particles, and therefore could use my model to describe the systems. So to conclude, I may say that my model allows to reduce the complexity of the mathematical techniques which are necessary to get at least a qualitative description of the electrostatic force. By that, in the hope that everyone has got some interesting insights into the world of quantum electrodynamics, I thank you all for your attention, and I'm open for your questions.
Hello, Moritz.
Hello.
Thank you for joining us on the comfortable couch. We're going to have a relaxed interview now after your presentation. I hope it went well.
Yes, I think so.
Very good. We saw it, and it seemed that it went very well.
That's nice.
So you talked about physics, right?
Yes.
It seems to be your field. Now, imagine that you had to explain to your grandmother in 1 or 2 sentences what is quantum physics, because not all of us know about it.
So quantum physics describes really the world at the tiniest stage. It's completely counterintuitive and allows to get a lot of new insights into this world, which is not accessible with classical physics.
Exactly, as you say, it's very theoretical and very small. You cannot see it. What fascinates you about this?
I think it's exactly that, because you have no intuition about it, and by theoretical analysis and mathematical techniques, you can construct, in fact, this new world, and it's really nice to see how the world really works at this tiny stage.
Very good. Now, I don't remember learning about quantum physics in high school. I don't think it's on the program. Now, where do you get your knowledge from? What resources do you use?
Yes, so physics is really my hobby, and I read a lot of books about it. And so, in fact, the initial book which brought me also to this project was the 3rd volume of the Feynman Lectures on Physics, a quite well-known book. And so there Mr. Feynman explains this topic in a really nice way, and so that's one of my main resources I use.
Very good.
So is Richard Feynman one of your heroes?
Yes, I think that he shaped, of course, the world of physics, and that he can explain things very, very well. Therefore, his lectures are also very well known.
Absolutely. And Feynman used to say, well, actually, nobody understands quantum mechanics. You just get used to it, in fact. Do you feel the same?
I think you have this world which is completely counterintuitive, but for me, understanding is also having this mathematical proof and seeing that that in fact, mathematics is a tool which is used to translate logic. And so when the mathematical proof works, one sees that the logic behind it works also.
Actually, Feynman added to his quote, "Shut up and calculate." And this is exactly what you've done. You know, you haven't questioned so much the interpretation, but you show that mathematically, formally, it works. It works as it should be. And that's really how now theorists vision physics nowadays. Now, last year you participated with a project that had some experimental aspect in it. It was about a reservoir of a rocket, an air rocket. So last year you did both experiment and theory. Now this year it's pure theory, right?
Yes.
Do you feel just as comfortable in both fields? Experiment, theory, or do you have a preference?
Yes, I think I have a preference for theory, because I really like the mathematics and the logic and this constructing a world only with equations and so on. But it is, of course, also important to have people who do the experiments, because without experiments, science would not be the same.
I knew you were going to say that. So I have another question now. I see you're so interested by the math, the mathematical aspects. Why did you choose physics at all and not just pure mathematics, you know?
Because for me, mathematics is only a tool, and the great thing about physics is that you can really predict what's happening in the real world. So you put up a theory with logic, mathematical techniques, and then you can really say what is going to happen, and that's the great thing about physics.
Now, I had the chance to interview you last year and now this year, and I'm very curious to hear what you're going to present us next year, if you're going to participate.
Yes, so if I'm going to participate, I don't know if it will be another project, but it could also be this project only with more precise results. So there are some details which could be improved because there are discrepancies between my model and, for example, Coulomb's force and so on. And there are also, of course, unanswered questions in this model, which would be very interesting to look at.
Yeah, I'm very curious now to hear what you're going to present us, if you're going to participate again next year. So one last question. What is the best moment you've had so far in the Young Fuerscher contest?
I always like the moment on stage because you can present your project to a public, to the jury, and really show what you have done. And it's great to stand there and do what you like, in fact.
I'm very surprised about that because most people would say being on stage is the worst, but very good that you like it. You did a good job too. Thank you.
Thank you. Congratulations again.
Thank you.